hand this over to you directly without.
Thank you. So I'm very, very happy to be at this center about which I've heard a lot over the years. The first time I got to visit it and see it for what it is. And I appreciate the opportunity to talk about this work, which, like everything else, was done with Ashwin. So Ashwin and I collaborated on this some years back. So he's not here, but you can address all the difficult questions to Ashwin. And I will tell you about the part I usually can remember on my own. So I'm not responsible for factors of 2, pi, plus signs, minus signs, especially when I'm working with fermions. But I think I just want to tell you what the main point is. Everything else is a detail. Main point was, when I was visiting Berkeley, Ashwin told me a very interesting coincidence, and we were working on trying to understand the coincidence. So the coincidence is the equality of two rather different quantities. The first quantity is the following. That is a P plus IP superconductor. So can you see this in the back? Okay, so this is the P plus IP superconductor. This is the X1 direction. This is the X2 direction, and X3 is like that. The P plus IP superconductor lives in this plane, and let's pick a few points. And the state, I'm going to call it BCS state, whatever the superconducting wave function is. It has got components with 2 particles, 4, 6, any number of particles, because it's a superposition of different numbers. In particular, it's got a wave function in a sector with n particles. R are these points here. The R that I'm talking about is the mixture of X1 and X2. That phi, n particle thing, can be obtained by taking the vacuum, destroying fermions at points R1, Rn, acting on the BCS state. Right? This is how you pull out the wave function, because this wave function has got the Fock vacuum times some creation operators in the wave function, and this destroys those creation operators and returns you to the vacuum. The coefficient is the wave function. This is a standard way to extract the wave function. Now, for a problem like this, where n is not fixed, and I have any n in this problem, it's more useful to define a generating function, which is 0 integral j of x, psi of x, d to x. Because if you take this, you have assembled all the possible wave functions into the single entity. You take derivatives of this with respect to j and put j equal to 0, you will bring down powers of psi and you will extract the wave function. All right, this is the first thing. This wave function is equal to something else, which I will tell you. Something else is the following. If you go to the edge of a P plus IP superconductor, suppose this is the edge, then along the edge there's a Majorana fermion, and there's a space-time of the Majorana fermion rising out of this side. So it's got this axis here and a perpendicular X3 axis, and the Majorana fermion is a field theory which has got correlation functions which are also labeled by some R1, Rn, and they are the expectation values of the product of Majorana operators at R1, Rn. This is a standard field theory correlation function where you take the time-ordered product. This R1 is made up, these R's are made up of X2 and X3. Namely, I'm not good at drawing this picture. You should imagine a plane bounded by this line here at the edge and a time direction measured perpendicular to it. So on that plane, you can pick some points, maybe I'll give it another shot. Take this edge, and here is the time, and here is the Majorana living here. This is the space-time, the Majorana, and these coordinates R live there. What was pointed out was that this G and this phi are not only related the way you expect in a topological theory, that the bulk and the edge have a connection, but they're really equal. Phi and G are the same function. And that's a bit of a surprise because phi is a non-relativistic wave function of n particles. This is a relativistic field theory with some correlation functions, and they're exactly the same. And the question is, why is that the case? That's all I'm going to explain today. So this is a good time to ask if anybody has trouble with the statement that's being made. Whether you follow the proof or not, at least you should know what is being said. Yes? Let me just say that I'm drawing two pictures in one. One is just the superconductor without any edge. That's the x1, x2 plane, and these are the wave functions in that plane. Now, if you created an edge along the x2 axis and a Euclidean time measured perpendicular to that, that's where the Majorana fermion will live. The edge fermion lives in that space-time. It's got its own correlation functions, which are given by this G. I'm saying they are the same function of their arguments. The question is, how did this wave function also be the same as a correlation function? Yeah? No. This is the Majorana vacuum. Yeah, this is the Mach vacuum, and this is the vacuum for the Majorana field theory, whatever the vacuum is for that theory. So you can use a different symbol. Yes? Yeah. Yeah, so these are statements in the deep infrared region. Extreme low energy theory of everything is when you can show this equality. Yeah, it might. It might not be true if you if you introduce higher powers of k and x, derivatives of x, it may not be true. So when I do the derivation, you will see that everything is true in the limit of very, very low energies. That's going to be used all the time. So it's not an equality at every level. Yeah, that's right. Yeah, it's a chiral Majorana free field theory. Right. Pardon me? Yes, this is the Majorana field. Oh, I think maybe this is what you're saying. Sorry. You put this field operator at n places and take the expectation value.
Size are not the same.
No, look, unfortunately, there's only one or two symbols we have in physics, right? You heard the song, a psi is just a psi. So that's what it is. I know small psi, and I know big psi. And I'm going to need even more than the big psi. So you got to deduce from the context what I'm talking about. But if you have a question, I can explain it to you. This is the non-relativistic fermion destruction operator. This is the quantum field for the Majorana and Euclidean spacetime. Yes? That's right. Yeah, that's right. So that is understood, that each is in its own natural plane in which it lives. Yeah, the functional form is the same function. No, I don't. You can take the Euclidean time to go from minus to plus infinity.
Yes, so that's the right-hand side.
Yeah,
On the
and here also the P plus IP superconductor also lives in the entire X1, X2 plane.
But with some, but I thought there's a edge.
No, that's what I said. The superconductor that I'm talking about here does not have an edge. But if you created an edge, that edge would have a Majorana fermion. It would have its own field theory. And the field theory will have these correlations, and they happen to be. Thanks for pointing that out.
Okay, thanks.
So to prove this equality, you first have to think in terms of generating functions for all possible wave functions, which is here. Then you say, here's where we are. The guy that we want is again, I don't know how to call the Fock vacuum. So let 0 be the Fock vacuum. That's understood. So what we are going to do is to say this BCS state is going to be obtained by taking any initial state you want. This is all in Euclidean time, doing a time evolution from minus infinity to 0 using the BCS Hamiltonian. And we know in Euclidean field theory, if you wait long enough, any state will reduce to the ground state. So we can write the BCS state as whatever initial state you want times this propagator from minus infinity to 0. And at that point, this is x3, this is the coordinate x3 in this problem. At x3 equal to 0, we put this guy. Then for this one, I'm going to take any final state, take a propagator from infinity to 0. But this one is for a Hamiltonian with a very, very negative chemical potential that does not like to have any particles in it. So if you wait long enough, it'll turn you into a state with 0 particles in it. That is this vacuum state here. So I'm writing the left-hand state as coming from the future with this u. Right-hand state is coming from the past with this u. The difference is the Hamiltonian for this one is the BCS Hamiltonian, which likes to have some particles in it. This one is a Hamiltonian with a very negative chemical potential that does not have any particles in it. If you write all of this down, you can see the emergence of a path integral by putting all these things out. But let's look at the Hamiltonian that I'm going to use for the BCS theory. The Hamiltonian in momentum space will have something like d dagger k, c of minus k. And I have c of k, c dagger of minus k, minus mu, plus mu, a k1 minus ik2, k1 plus ik2. You can put some number like delta here, but that's not important. This is the Hamiltonian, and you take this guy and you write it in real space, where you're going to keep only the first derivatives. So that Hamiltonian in real space, you can see, will look like some psi dagger that's coming from the c dagger c terms minus mu times psi. Then you will have a psi dagger term with I times d means d by dz. D by dz is d by d of x plus iy, but x and y are the two coordinates here. The psi times I d bar psi. This is my Hamiltonian. What about mu? Mu can be chosen in this domain, in this region. Mu should be large and positive. In this region, mu should be large and negative. This Hamiltonian really does depend parametrically on time through mu. The mu that I want looks like this. Mu as a function of x3. The distant past has got a positive mu, enough particles to form the BCS state, and in the future, a very large negative mu that has no room for any particles. That's the kind of mu that you want. Now let us write the action for the Euclidean path integral. You can sort of read it off. So the action is going to look like minus d by d3 plus mu psi plus j of x1, x2, delta of x3, psi of x1, x2, x3, d3x. So again, I have to apologize for notation. When you take a fermionic Hamiltonian with some operators like psi, dagger, and psi, and use coherent state, fermionic coherent states, those states also carry labels like psi and psi bar. So if you act with psi dagger on the left, you pull out this eigenvalue. Acting on the right, you pull out this eigenvalue. So this psi bar and this psi bar is not like the psi bar in Dirac theory, like psi dagger, gamma naught. It is just the Grassmann variable associated with the bra, and this is the Grassmann variable associated with the ket. Yep. Yeah, that's correct. Yes. So now this is the theory we want to work with. And here's what I'm going to do. Look at this guy. It's some differential operator d, and the mu is a function of time. Beauty with Grassmann numbers is that psi bar and psi are not connected to each other in any way. You can integrate with respect to psi bar without doing anything to psi. And psi is the guy I'm interested in. The psi is the one that couples to my source. The psi bar is not connected to my source. So I can integrate out psi bar. That's a Gaussian integral. In the Gaussian integral, this is like the quadratic Gaussian action. This is like the field coupled to this Grassmann source. And you do the integral in your head, you can sort of see that what you will get will be this thing, d transpose d, divided by id psi, d bar psi, plus j delta x3, I d3x. This is just the completing the square and doing the Gaussian integral. Pardon me? Yes, yes, it's a Grassmann source. Well, all these psis depend on x1, x2, and x3, right? Because you had a Hamiltonian in 2 dimensions, and you're doing a path integral over Euclidean time, so that's the third argument. And the source enters only at time t equal to 0. Remember how I did the integral? So basically, particles come from the distant past, and at t equal to 0, they hit this plane, come from the distant past, and they get clobbered when they hit x3 equal to 0 plane. We refer to that as bugs on the windshield. If you drive a car at high speed, all the bugs hit the windshield and they get stuck there. That's what happens to this. Because J3 kills all of them here. Above that time, there is nothing. There is just a vacuum. So let's do this integral now. So in this integral, this is like a kinetic energy for this object. If you go to the low energy theory, that's the answer to your question. Everything here is extreme low energy. Extreme low energy, you want to find the mode which has the lowest energy for this, and you might know that if you got a potential that looks like this, and the Hamiltonian is minus d3 plus mu, that's a function f. It's called the Jacobi-Van-Rebbe solution, which is localized to be in the vicinity of this, and it has 0 energy. This is really like the harmonic oscillator without the 1/2 0-point energy, so that's exactly 0 energy solution here. Therefore, everything else has got much higher energy. Therefore, we will saturate this Grassmann field, psi of x1, x2, x3, as the 0 mode as a function of x3 times some coefficient x1, x2. So imagine doing that. If you take your field to be of this form, this is then gone because D annihilates this. Then this F0 will come along, and these are all derivatives involving only 1 and 2. So this will just go right through them, and F0 squared dx3 is 1. So it will disappear from the picture. Only here, that will be some j times f0 at x3 equal to 0, a constant. And you can choose f3 of 0 to be 1 if you like, and then you can forget all of that. So what I get in the end, the action for this looks like psi I d bar psi plus j psi d2x. There is no x3 in this picture. You can see that this is the effective action for a chiral Majorana fermion. This is the chiral Majorana fermion coupled to a source. So Z of j is really now, you can already see, is the source term for a chiral Majorana theory. It's morphed from being generator of wave functions to the generator of correlations functions to the Majorana theory. If you want to do the Gaussian integral, you can, and the answer will look like j 1 over id j, and that'll become Pfaffian of 1 over zi minus zj, which one knows is the wave function for the p plus ip superconductor. But that's not enough for me. I want to show you that, yes, this happens to be the p plus ip superconductor wave function. It also looks like a Majorana field theory, but I want to show you this is the same Majorana that comes at the edge of my original p plus ip superconductor. So how do you show that? For that, you go back a little bit to some earlier stage, like here. Go to this stage and introduce now, I'm again at a loss for symbols, so this is a big psi. This is a psi held by Lord Vishnu. This psi got two parts, psi and a psi bar. So it's a two-component spinner. Yes? Yeah? No. No, it's a topological guaranteed zero mode. So that part is robust. You will have that zero mode. But finite energy stuff has been dropped left and right, so I'm not responsible for that. This is the extreme low energy characterization. So you form now a two-component field like that. Then you take this operator here and write it in terms of these two components. So not here, I'm sorry, you go back to an earlier stage when I had psi and psi bar in it. Go here. Then you can write it as this big psi bar times d slash minus mu big psi plus j times big psi, where j will contain only the upper component times delta function of x3 times d3x. So in case you're wondering where we are going going back a few steps to this form of the action and forming psi bar as a two-component spinner, the big super psi, and writing it in that form, then you can turn it into what looks like a Dirac theory. And this psi bar is the old psi transpose times the epsilon matrix, which is the 1 minus 1 matrix. Because you know that the chemical potential mu in a Dirac theory should not couple to any gamma matrices. The original theory, it's got some minus signs, and you absorb that in the psi bar and make it psi transpose and make it psi bar, so that this looks like a scalar. So we are almost done now, because here is where we stand. You have a Dirac theory, and you have a source, and the derivatives with respect to source are the wave functions of the original theory. And that looks like this. Draw this here. My original problem, where the BCS is living here. This is the surface where the J kills all the fermions. And this is the region where there is no particles here at all. This is the Fock vacuum. And this is the X3 direction. But this action now here is Lorentz invariant, the way it's been written. So I can do a rotation around this X2 axis and turn this guy on the side. If I turn this guy on the side, you just put primes on everything because it'll be invariant. Only thing that happens to J changes into the 1I divided by root 2 under that rotation in Lorentz space. The points carry the same label, so I tilt this guy on the side, it looks like this. So now, this is the x3 direction. This has got the BCS, this has got the vacuum. Now, this is a system with a real edge now. That used to be in Euclidean space-time between negative times and positive time, there's a dividing line. Here, in this sample, it's a BCS superconductor with an edge. And this wall is the one that keeps particles from crossing over to the vacuum. Therefore, all you have to do is, in this theory, the J couples to a field psi plus I psi bar over root 2 and finds the correlation functions. They are precisely the correlation functions of the edge of this BCS superconductor. So what we did then, we took a Z of J, which starts out by generating the wave functions of the BCS theory. You write it as a relativistic theory, then you rotate this whole chunk of space-time so it looks like this, and what used to be a jump in time of the chemical potential becomes a jump in space of the chemical potential, creating an edge. But Z has remained unchanged throughout, except the fact that it couples there to psi, and here it couples to psi plus I psi bar, which are the correct quantum numbers of the Majorana at the edge. So that is the explanation of how this happens. But I want to emphasize that this is not due to conformal invariance. This may be a scale invariant theory, but it's really connected to Lorentz invariance. Because there's another example in one higher dimensions, that's the helium B space. There, you will again have a quadratic kinetic term, all the mu's and so on. But what comes here will be K dot sigma. Sigma is the real spin of the fermions in this problem. So what used to be a complex number in the old problem, kx plus iky, becomes a quaternion in this higher dimensional problem. And everything is exactly the same. You will have a Dirac equation in 3 dimensions, then you turn it into 4 dimensions, and then you do a rotation. And then the correlation functions of this theory will be some Pfaffian of 1 over K dot sigma, which in real space look like Ri minus Rj divided by sigma dot Ra minus Rj divided by Ra minus Rj cubed Pfaffian. So that's another problem in one higher dimensions where you can do exactly the same thing. Where also the bulk and the edge have exactly the same functions connected with them. And the reason for that is that with one more dimension, this is going to be another Dirac theory with one more derivative, one more gamma matrix, but you can do everything that I did before, do the same rotation. And there also you will find it miraculously, J turns into the right quantum numbers for the field at the edge of that superconductor. 0 more dimension independent. Because all you will do in this picture, you will take this region to be 3-dimensional with the jump in chemical potential as a function of Euclidean time, and you will max out that with the 0 mode of that. So that will not depend on how many spatial dimensions you have. Then you can also go to one lower dimension. You can go to lower dimension where the chiral Majorana fermion has some Lagrangian that looks like this. Also, so you can go to any number of dimensions where you have the linearized dispersion relation in this term, and you got some kind of a Dirac theory then whose invariance allows you to relate the bulk and the edge. So this is Lorentz invariance is the reason behind this. So we cannot do this in something like the quantum Hall effect and say anything about its edge. Because you need a theory where particle number is not sacred. You want to time evolve a system and suddenly kill all the particle it has. You can never do that in something like the Laughlin problem where particles are conserved. You need something like a BCS theory where there's a chemical potential but no constraint on the particle number, so you can produce the Fock vacuum on demand by tuning the chemical potential. So we couldn't learn anything about any other problems. For a more detailed classification of where this can happen, you should read our paper or talk to Ashwin, because I have no idea what he's talking about. Let me tell you what the man says. He says class C1 in D equal to 3 and class D3 in D equal to 2 and 3. I don't know what that is, but I believe it's more of the same. So I'll stop now and answer questions. Thank you.
Questions?
So I understand the argument, or this line of arguments doesn't work for the quantum Hall.
Yes.
But still, there seems to be some relation between conformal blocks in the bulk and
Okay, look,
the
you
edge.
can take any Euclidean theory and do a rotation, right? No one can stop you from doing it. But what can happen sometimes, if it has got second or third derivatives in space in one, you'll have second or third derivatives of space, of time in the other one. So it may map one problem to the edge of a different problem.
So is this a way to understand this bulk edge correspondence in the quantum Hall, at least at the level of a Laughlin wave function?
No, I don't know how to do that using this trick. Because I don't see Lorentz invariant in anywhere in the microscopic Hamiltonian for the quantum Hall problem. It's a BCS that tends to have linear derivatives very naturally, so I can get a Dirac theory. But you can have some other theory. Even if it's not Lorentz invariant, you can always rotate any problem, right? You have a row-to-row transfer matrix that describes one physics, turn it on the side. You have a column-to-column transfer matrix that describes usually a different problem. You can always relate one problem to another problem. This is like self-duality, where you relate one problem to the same problem. Therefore, learn something about the edge of the very same problem.
And if you do the rotation on a Laughlin wave function, where does it take you to?
Nowhere I want to be alone, because it took us to some crazy place. We couldn't make any sense out of the rotated Hamiltonian. I should say one more thing, which is it is known that the edge captures the entanglement properties of the bulk. But here we find that the edge reflects back on the bulk itself. So knowing a tiny sliver of the bulk, you can say everything about the whole bulk in these theories. Every tiny sliver of the bulk contains information over the entire one. That's another kind of holography where you just need a piece of that to reconstruct the whole thing. Yes?
I was listening to, I was reminded of a old work by Krishnendu Sengupta and Yakavenko.
Yeah.
May have some relevance. What they did was, they took P plus IP superconductor. On one side, they created a domain wall. They had P minus IP
Uh-huh.
on the other side. So they found a beautiful free Majorana mode along the line. In fact, this was one of the first time when Majorana fermion appeared in condensed matter context,
I see.
well before Kitaev chain and so on.
Uh,
So it may have some relevance.
Quite possible, that's correct. So I have to see what to do to the P plus IP to turn it into P minus IP.
Exactly. Yeah.
I know that by cranking up the chemical potential to deep negative values, I can turn P plus IP to vacuum. You want to turn it into P minus IP, I don't know what I should put there.
They get Majorana Fermi C along the line.
No, but what do? They just glue them together, you mean?
So the domain wall solution.
I see, yeah.
So on one side you have
Oh, I see.
polyton.
Mm-hmm. Right.
They find
Yep.
Yakavenko and Krishnendu Sen.
Questions? Yeah.
So this is a mapping between boundary at the constant time slice and
Yeah.
constant space
That's right.
slice. So suppose I have physical boundary, which is a boundary at the constant space slice. Then you measure a wave function near this boundary. Then you have sort of two edges, perpendicular edges, constant time plus constant space. I guess if you can still rotate this 45 can we use this
Uh,
something?
I don't fully understand because I'm not good at thinking on my feet. So you want me to make one cut this way and another cut that way?
Yeah, if we have two surfaces,
Yeah.
probably that can
Right.
be related to wave function near the boundary.
Look, I don't know offhand. But I know that if you have some way to play with the chemical potential to engineer what you wanted, yeah, you could have a chemical potential that even in the original problem varies in space. And you can have it also vary in time. So you create a system with an edge in space and in time. You could do that, then you can rotate it and see what you get. I think that part will go through, but I don't know what will be related to what by doing that.
Any other questions?
Yeah.
Out I.
Pardon me? Yes.
I plus
No, I think in this problem it is I psi bar, remember correctly. Well, if you, no, but if you go, Majorana depends on the basis you're using. It's dependent on the basis. If you take this Hamiltonian and you do the rotation and solve for the edge mode in a problem with a real edge, you will find that mode is the 1I mode, not 1-1 mode, psi and psi bar.
Any other questions? Okay.
Listening to it was not obvious to me that a P plus IP superconductor surface will be Majorana Fermi. Is that, are you also providing a proof for that?
You mean if you have a vortex or something?
No, without vortex. Suppose I
Yeah.
take
Yeah.
the surface. Whatever you are saying, I see that there is a surface.
No,
edge
no.
Majorana.
You'll have to create an edge for the
Edge.
Majorana. It won't be there in the bulk.
So in the edge, you are saying that there is a Majorana.
Yes, that's right.
Is it obvious that?
Yeah, you can solve this
Okay,
BCS
so you get
theory
it
at the
after
edge.
solving this. Okay.
Solve for the edge mode. Again, you will be working with this Jakiv and Rebbe mode near the edge, and you will find the solution is this Majorana fermion. The same f of x3. I think it's time to thank the speaker and go to lunch. Yes. Okay. Bye-bye.